We're going to do practice problems 2.3 in B1, work, energy, and power. I'm not doing all of these problems. I'm just going to focus on the IB questions. So that includes number 3, number 7, 8, 9, 10, 11, and 16, since a lot of people have problems with 16. So let's start. A student makes 3 statements about situations in which no work is done on an object. Statement number 1, the object is moving with uniform circular motion. Statement number 2, a force is applied to the object in the direction of its velocity. And statement number 3, a force is applied to the object in a direction opposite to its motion. Which of the above statements are correct? Remember our equation for work. Work is F S cosine theta. The force is applied parallel or anti-parallel to the displacement. For an object moving in circular motion, there are 2 ways you can rationalize this. Either you know that the net force on an object moving in a uniform circle is the centripetal force. Any point on the circle, its displacement is always perpendicular to the force. So cosine of 90 degrees is 0. Or you could think about a uniform circle. If an object moves in a circle, displacement is 0. So either way, no work is done. So this statement is correct. Number 1 is correct. Number 2, a force is applied to the object in the direction of its velocity. So if we have a force applied over some displacement, this is work. If we have force applied while in the same direction as an object is moving, that is work being done to the object. So this is an incorrect statement. Force is applied to the object in a direction opposite to its motion. This is just negative work. W cosine of 180 degrees. Let's say I have a force going one way, but the object is being displaced the other. Then negative work is being done to the object. So work is still being done, so only number 1 is correct. Okay. Number 7, the graph shows how the acceleration of an object how the acceleration A of an object varies with distance traveled x. So this is a graph of A. The units are meters per second squared versus x in meters. The mass of the object is 5 kilograms. What is the total work done on the object? So work is force times displacement cosine theta. We can neglect this cosine theta part and we can calculate the area under the curve. The area under a force versus displacement curve is the work. In this case, though, I have acceleration. So you will calculate the area for this rectangle and the area for this triangle. Again, this is 1/2 base times height. You're going to add these 2 areas, but what you get is not the work. Instead, you've just multiplied acceleration times displacement. You know what? You need mass to get work. You will then multiply your resulting area by 5, and this will tell you the work. Okay, number 8, a 4 kilogram ball is thrown downwards with an initial kinetic energy of 200 joules. What is the distance fallen by the object when the kinetic energy has doubled? So this is energy conservation, and I know that the kinetic energy, the change in kinetic energy will equal a negative change in potential energy. And I'm sorry, I keep doing E sub k. So a change in kinetic energy equals negative E sub p, because according to energy conservation, the sum of the change in kinetic plus the sum of the sum of the change in kinetic and potential energy is 0. So that's how I know this relation is true. So initially I have 200 joules, and finally this kinetic energy is doubled, so 200 times 2 is 400 joules, so I have 400 minus 200 equals a negative change in potential energy. So negative mg delta h, it's 4 kilograms, so I have 200 joules equals, I'll use g as 10, negative 40 times delta h. I'll solve for delta h. Delta h will tell me displacement, and I want the distance, so then I just take the absolute value. In this case, 5 meters it has fallen. Okay, next. Number 9, a solid 1.3 kilogram ball rolls from rest down a ramp without slipping. The ramp is 0.15 meters high and the radius of the sphere is 4.5 centimeters. What is the speed of the ball at the bottom of the ramp? The moment of inertia of a sphere is 2/5 mr squared. So this is like our torque problems continued. So let's see. In this case, it's actually a lot easier though, because I know that for this object, the potential energy at the start, E sub P, supplies all of the energy for all of the kinetic energy at the bottom. There's no kinetic energy at the start, and there's no potential energy at the bottom. So I know that EP initial equals E sub K final. Potential energy at the start equals kinetic energy at the bottom of the ramp. Now, kinetic energy has two forms. Kinetic energy can be linear, and we have rotational kinetic energy. In this case, an object rolling down a ramp has both. So I have EPI is the mass of the object times gravity times its height equals 1/2 mv squared. This is the linear kinetic energy plus its rotational kinetic energy, 1/2 I omega squared. And now I don't have omega, but omega, and just like how alpha is related to linear acceleration, omega is related to linear velocity. In this case, omega equals v over r. So I'm going to replace this omega with v over r. So I have mgh equals 1/2 mv squared plus 1/2 I, which is 2/5 mr squared, 2 over 5 times 2/5 mr squared times omega squared, which is v over r squared. Hopefully you can see that. This is the potential energy plus 1/2 mv squared plus 1/2 times 2/5 mr squared. This is the moment of inertia equation, times omega squared, and I replaced omega with v over r. Now you can see all of my m terms cancel. I don't even need the mass to solve this, and so I will simplify. I'm looking for final velocity, which is already given here, and it's combined on one side of the equation. So I have g times h equals 1/2 v squared plus 1/2 times 2/5, that's 2/10, times r squared times v squared over r squared. So all of the r squareds cancel times v squared. This simplifies really nicely. So I have gh equals 1/2 plus 2/10. 1/2 is 5/10. So I have 7/10 times v squared. And from here you should easily be able to solve for v, given g as 10 meters per second squared and the height of the ramp 0.15 meters. Multiply by 10, divide by 7, get the v squared, and then take the square root. From here, I think you got it. So I'll rewrite this. mgh became the linear kinetic energy plus the rotational kinetic energy. The linear plus the rotational is an object's total kinetic energy. Okay, number 10. Ms. Rancifero's demo used two different discs of the same size and mass. In one disc, she placed weights very close to the axis of rotation. So this was the axis of rotation, and I had this demo where I had weights that were distributed along the rim, and I had weights that were distributed near the axis of rotation, and I allowed these two cylinders to roll down a ramp, and both of them have the same mass. Both of them have the same size. The only difference is where I place the ball bearings inside of these discs. The disc that rolls down faster, it was this one. This disc rolled faster. And why was that? The reason is because this disc has a smaller moment of inertia. More of the potential energy could go into this object's linear, could become this disk's linear kinetic energy. This object had more resistance to changing its rotation. It had a higher moment of inertia. Moment of inertia is mr squared. So if I have mass distributed further from the axis of rotation, I've increased the moment of inertia. So this object resisted rolling, and that's the only thing that got these two down the ramp. More of the potential energy had to go into rotating this object versus this object rotated faster, got down the ramp faster. So, and that's why. Because masses were near axis of rotation. Okay, that's good. All right. Number 11, a system that consists of a single spring stores a total elastic potential energy E sub P when a load is added to the spring. Another identical spring connected in parallel is added to the system. The same load is now applied to the parallel springs. What is the resulting EP, the elastic potential energy in the changing system? So we need an equation that IB does not provide. It is F equals negative kx. This is the spring force. I'll go more into springs when we get to topic 4. For now, just disregard this negative sign. It just means that a force, the spring force, is a restoring force. It tries to do whatever, it tries to do the opposite of whatever you do to a spring. So if you compress a spring, it tries to push out. If you pull a spring, it tries to push in. Okay, so I'll just simplify this expression, F equals kx. And the reason I need this equation is to figure out how the displacement of the spring changes when I have a load like this resting on one spring with a spring constant versus two identical springs like that bearing this load together in parallel. So if I say that this spring, it has a spring constant K, it has this load on it, this F, that means that the displacement of the spring is x. I'll just make that a constant. What happens then if I add a spring in parallel? Well, I still have the same load, the same force of gravity, which the two springs must oppose, but now each spring only supports F over 2. Each spring only has to oppose half of that force because I have two springs in parallel. And if I think about a free body diagram for this situation, this is in equilibrium. There are no oscillations, system is at rest, then the sum of the two forces exerted by the spring should equal the load, which means that each spring bears half the load. F over 2 plus F over 2 is F. So all of my y forces cancel. Well, what does that mean regarding the displacement? Each one spring has F over 2 load. The K, the spring constant, is a constant. It doesn't change. So to make this equation true on both sides, the spring is only displaced now by 1/2 the original value. Half of the load on the spring means half of the displacement. So let's now look at the equation for potential energy. The elastic potential energy of a spring, E sub P, is 1/2 kx squared, where x is the displacement. So if we had our original value, okay, this is my original potential energy. Now, what happens when I have x over 2? If I just look at one spring for one spring, let's see what this looks like. My E sub P equals 1/2 times K, that's a constant, it doesn't change, times half of the displacement squared, open parentheses, x over 2 squared. This becomes 1/2 times K times x squared over 2 squared. This is 1/2 times K times x squared over 4. This reduces to 1 over 8 times K times x squared. I have two springs like this, not just one. So for a system of two springs, I double this. So for two springs, it is 2 times this potential. 2 times 1 over 8 times kx squared reduces to 1 over 4 kx squared for the potential energy of the system with two springs. Compare 1/4 kx squared versus 1/2 kx squared. A fourth is 1/2 of a half. So what is the resulting E sub p in the change system? It is this value, the resulting E sub p. So E sub p is reduced by 1/2. And so I had that, 1/4 kx squared. Okay, 12, 13, 14, 15 you should do. Number 16, a lot of people missed or have missed in the past, so let's go over it. The efficiency of an electric motor is 25%. So eta, this is the Greek letter, it looks like an N with a long tail, equals 0.25. When lifting a body, 5,400 joules of energy are wasted. Energy is wasted in the form of heat. What is the useful work done by the motor? So the useful work done by the motor, to figure that out, we have to use our efficiency equation. Efficiency is useful work out divided by total energy in. The total energy into the system contains heat plus the work out. I'm using the symbol Q for heat, divided by the work out. So I'm looking for work out. What I can do is invert this equation, or I can say that this is equal to 0.25. I can multiply by work out on both sides, or I can just invert both sides of the equation, which is what I prefer to do. So I'm going to do work out plus Q divided by work out equals 1 over 0.25. This becomes 1 plus Q over work out equals 1 over 0.25. I have 5,400 joules. I'm looking for work out. You can finish the rest of this. I hope you found this video helpful. Thanks for watching and study well.